So remember, we talked about the amount of substance, a small reminder about the atomic mass, molecular mass.
Why is Bill here?
Oh, am I lagging?
I cannot hear your voice. A difference.
Okay, wait, let me see the Wi-Fi. Okay, I'm already connected to the correct one. So I think we'll just have to, just tell me if I'm lagging, so I'll pause.
Okay.
Yeah, so we looked at how to calculate the molecular mass. We just add the atomic masses of all the atoms inside one molecule, and we find the molecular mass. And then the last thing, before I started, I stopped off at the Avogadro constant, because this is like, you cannot, once you start, you cannot stop it, or else it's really confusing. Okay, so essentially the Avogadro constant is like a way of measuring atoms because they're too small. So when I ask a chemist, how many atoms are there in this amount of solid? It takes too long to say something like, oh, there are 500 million billion atoms. So the Avogadro constant, a lot like the molecular mass, is a way of shortening the big numbers. So one atom is too small to measure. The mass is too small to measure. Everything about it is too small to measure. So usually chemists consider a large number of atoms at once. Imagine a bit like megabytes, gigabytes. 1 byte in terms of your computer is like nothing. You can't do anything with 1 byte. So normally when we consider data, when we consider memory, we say something like, oh, it's 10 megabytes, it's 1 gigabyte. We don't have to say there are 10,000 bytes because we just shorten it to megabyte. So this is a little bit like this. It's just to help you understand really big amounts of particles. Okay, so before we come back to the Avogadro constant, I want to introduce the concept of number of atoms in amount of substance. So for hydrogen, the atomic mass is 1 because I think the atomic mass is if you look at the periodic table, you have those numbers on the top. So those are the atomic numbers, but the atomic mass is the same. Well, it's almost the same as that. It's like 1.1. So the atomic mass of hydrogen is 1. And the atomic mass of helium is 4 because it has 2 protons and 2 neutrons. And when I say I have 1 gram of hydrogen, because the relative atomic mass of hydrogen is 1, then the number of atoms in 1 gram of hydrogen is the same as the number of atoms in 4 grams of helium. Does this kind of make sense? Why it's this like this? So maybe an easy way to consider this is if I have an apple and the apple is 10 grams. 10 grams. And I have an orange. The orange is slightly smaller. And the orange is 7 grams. So if I have 10 grams of apples, well, not 10 grams, let's just say I have 100 grams of apples. How many apples do I have in this amount?
What was that, Miss?
So 1 apple is 10 grams. 1 orange is 7 grams. So how many apples do I have in 100 grams?
70 orange.
No, apples.
Oh,
So
apples.
Oh,
10.
10. So I have 10 apples, right? So what about oranges? If I have 70 grams of oranges, how many oranges do I have?
10.
10, yes. Now, with atoms, if one hydrogen is 1 AMU and one helium is 4. So does 1 gram of hydrogen, does it have the same amount as, this is not 1, there should be 4 grams of helium? So you don't have to know how many there are, but do they have the same amount?
No.
How come? Why no? So if one helium is 4 times the mass of hydrogen, and now I have 4 times the mass of helium, 4 times the mass of hydrogen, do you think these two weights have the same number of particles? What do you think? Yes, they do. They have the same number of atoms in them. So for example, I have another example. If I have maybe something easier, again with my apples and oranges. So if I have an apple, and one apple contains, let's say, 1 gram, an orange, well, an apple is going to be heavier. So a melon, this is just an example, an apple is not 1 gram, it's 4 grams. If I have 1 kilogram of apples, how many apples do I have? So 1 apple is 1 gram. How many is there in 1 kilogram? Guys? How many?
So just divide it, right?
Yeah, just divide it. How many are there? So 1 kilogram is how many grams?
100.
1,000?
1,000.
Oh, 1,000.
Yes, so how many apples are there in 1 kilogram of apples?
Apples
1,000.
in
Yes,
1 gram.
1,000. 1,000 apples, right?
Yeah.
So if I have, I'm just gonna move this here. So if I have 4 kilos of oranges, how many oranges do I have?
1,000.
Yes, 1,000, the same, right? So do I have the same
Ah.
number of apples and oranges?
I see. Yes, you do.
Yes. So now if I change the names of things, I change it slightly. So instead of apple, now I have hydrogen. 1 hydrogen is 1 AMU. 1 helium is 4 AMU. Now if I have 1 gram of hydrogen, I don't need to know how many there are, and 4 grams of helium. Do you think these have the same amount of atoms inside them?
Yes.
Yes, yes, right? Because it's times 4. This is times 4. So of course, this is also times 4. So it should be the same. So the same thing, instead of hydrogen, I have water. So the molecular mass of water is 18. How come? Water is H2O. Hydrogen, the atomic mass of hydrogen is 1. And then I have 2 hydrogens, so it's 1 plus 1. And of oxygen, it's 16. So it's 1 plus 1 plus 16. So water has 18 AMU. So it's because hydrogen is 1 AMU and water is 18. Of course, there's going to be the same number of atoms of hydrogen in 1 gram as there are molecules of water in 18 grams. So this makes sense, right? Instead of, so I just changed this to H2O, and that's 18. And then all of these have the same number of particles. So I say particles because it's either atoms or molecules, because water is a molecule, not an atom. So all of these have the same number of particles. So now the question is, how many atoms are there in 1 gram of hydrogen? So with apples, like before, we just divide the mass with the mass of 1 apple. But how do we know how many atoms there are in 1 gram of hydrogen and in 4 grams of helium? So I know that all of these contain the same number of atoms, but how many is that? How many particles are there? So this is how we find out. In all of these, there are these many atoms or molecules. So if I have an atom that's 1 AMU, in 1 gram, there is this much. If I have an atom that's 7 AMU, in 7 grams, there's this much. So you can see it has to be the same thing. 1 AMU, 1 gram, 7 AMU, 7 gram, 10 AMU, 10 gram. So in that, there are these many atoms or molecules. Does that kind of make sense? Or do you want me to repeat it? Repeat it one more time? Or is it okay?
Can you repeat it, Miss?
Yes, repeat it. Okay, so if I have 1 gram, 1 AMU of some, if one atom's mass is 1 AMU, and I have 1 gram of sample, then how many atoms are there in this? I divide it, right? 1 AMU. So remember from last time, there was a way of converting 1 AMU to grams. So this is the shortcut. This is the answer. If I have something that weighs 7 AMU, and I have 7 grams of it, to find out how many there are in these 7 grams, I divide it, right? 7 gram divided by 7 AMU. And the answer is this. That's the answer. The same thing. So I'm just going to give you an example of something you're familiar with. If one apple, the weight of one apple is 1 gram, and I have 1,000 grams, then to know how many apples there are in this one, I just divide it, right? So it's one apple weighs 1. I have 1,000. I have a bag with 1,000 apples. I just divide it, so it means I have 1,000 apples, like this. So I know this because I know exactly the mass of this. But for atoms, I don't know. Well, it's hard for me to remember how many grams AMU is. So the shortcut is if the mass in grams and the mass in AMU is the same. So if I have X, if one atom is X AMU, so X is any number, and I have X grams of it, then the number of atoms in total, is this. It's just a way for me to remember it easily. So for hydrogen, the atom is 1 AMU. Then because the X has to be the same, then of course, in 1 gram, there are these number of atoms. For water, one molecule is 18, So of course, in 18 grams, it has to be the same. I have this number of molecules. So imagine 18 grams of water is actually not so small. I can see it. It's like maybe a teaspoon of water. So in my teaspoon of water, how many molecules of water are there? The answer is there are this much. So like 18 grams of water is like maybe 10 drops of water. So there are this much molecules. Was that a bit clear?
Yes.
Yes, everybody else? Rashi, is that okay? Yeah, Rashi, Sharon, FN.
Yes, miss.
Yeah.
Yes.
Okay, so what is this number called? That number is called the Avogadro constant. So 6.022 times 10 to the power 23. This is the Avogadro constant. And it's defined as the number of atoms in 12 grams of carbon-12. Why carbon-12? Well, because the weight, the atomic mass of carbon-12 is 12 AMU. So the same thing like before. So of course, the same number in 12 grams of carbon-12, there are going to be this many atoms. So you see, it's the same number, carbon-12 and 12 grams. Okay. Here's some examples. In 1 gram of hydrogen, which is atomic mass 1, there are as many. In 4 grams of carbon dioxide, this is a different example. The molecular mass of carbon dioxide is 44. So of course, in 44 grams, there are also this much. And helium, atomic mass 4 grams, it has to be the same. There are this many atoms, and so forth. Okay. So if you guys would like to try classwork 2.1-2, just to help you practice this, so you don't forget it. So wait, let me see if I can show it to you guys. Classwork 2.1. It should be this. So let me know if you cannot find it. This one. So let me know if you cannot find it or you cannot open it for some reason. And also let me know if you're confused with the question.
Miss, how to find MU, Miss? I forgot, Miss.
So you see how in the top of the question, there's like 1 AMU equals to this many grams.
Yeah.
So you just convert it. You just use that equation. So if I have grams, I just divide it, right?
Yeah, Miss. Thank you, Miss.
Yep.